Hey, hi, this is Kunal, and today I'm going to discuss on implementing house price predictions using the linear regression with regression technique called build the model. So basically, what is the requirement we have is that a US-based housing company named Surprise Housing has decided to enter the Australian market, and the company used data analytics to purchase houses at a price below the actual house and flip them in a higher price. For the same purpose, the company has collected a data set from the sales of house in Australia, and the data is provided in the CSV file. The company is looking at the prospective properties to buy to enter the market. You are required to build a regression model using the regularization in order to predict the actual value. So it's clearly mentioning that we have to build a regression model using the regularization to predict the actual value of the prospective properties and decide whether to invest them or not. So company wants to know which variables are significant in order to predict the house of the price and house of the price and how well those variables describe the price of a house. Also determine the actual value of the lambda for region lasso regression. Basically, we have to build the model for the price of house with available independent variable. The model will be then used by management to understand how exactly the price vary with this variable. Then can accordingly manipulate the strategy of the farming consider the area that yield high returns. Further, the model will be a good way for management to understand the pricing dynamics of a new market. Okay, so let's see for any before building any data, I mean any model, we have to understand the data and clean it, and also we need to transform into the a standard format using a standard scalar or min-max scalar. And we also need to remove the outlier if it is percent. We have to impute any missing value there. So we will going through all those steps here. So let's see if there's any header or footer or present in the data or not. We are checking the housing dot header. It will see that there's any header or present not. So there is no header here, and there is no any footer was also present here. Let's check if there's a data is duplicated or not. So there is no duplicate data exist. Since ID is a unique in nature, we can drop it. Let's check if there's any, we have a uniqueness into the columns or not. And we don't find any unique columns. Any columns meant the column which is having all the values are for every row the values are different. That is called unique columns, and we don't have such kind of columns because if all the values are different for each rows, then it is meaningless for use them into the model because it will not give any meaningful information for the model. Here we are trying to see if there's a how I mean how many data points we have for each of the other column. So for the street we have a tool, I mean different data points. We can say the unique data point, the street to LA2 related to, and this seems to be categorical values. And here we are having the numerical values, so we can also check it. And let's see if there's any null value present into the data, right? So we can see that around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 column which is having the null values. So we see how we are going to treat them. How we are going to treat the null value here. So one approach we will use for treating the null value. We will use separate approach for numerical value and separate approach for categorical value. We are driving one more feature because if it is if you go with the a real estate thing, so how old a house is, right? So that give more informations about the price of the a house, because older the house, it is going to be less the price. Always a new house is having the high prices. So that is the reason we had to write one more feature. And we can, since pool QC have all the rows as well, so we can drop it. And since we have already used year sold and year built, so we can drop those columns because we have already derived this column. And if we keep it those columns along with it, it will create a multi-collinearity problem. So that's better to drop them and see. Still, we have to check it here. We also have some plans over the data and see if there is any outlier present into it or not. So we can clearly see that from 99.5 to 160, and then suddenly it's spiked into the 90. Here is a 313 and 141. If you check it here, and then this seems to be good, but this data surely have a lot of outliers. You can check it out. These are seems to be high outlier for every most of the columns. So here we are dividing the data into the two part, housing, numeric part into the categorical part, as we discussed earlier. And we are going to handle the missing value differently. So for categorical column, we see what are the feature they are having the value as a null. So from the data dictionary, what we can inference that NA represent the facility not available. It is not that data is missing there, but it means that the data is that facility is not available for that particular houses. So that is the reason it is mentioned as NA. So what we are going to do, instead of NA, we are going to impute with NaN. Okay, so and we'll also check if it is a housing or there is a numeric column also. So see if there's how many of feature are having the null value for numeric column as well. And one thing while imputing the missing value with the numeric value, what we can see that since the area is a state connected to the housing property, most likely to have a similar area to other housing to the neighborhood. So we can fill in the missing value by median foot lot frontage of the neighborhood. We'll take the sum of the neighborhood house and take the median of the lot frontage of the neighborhood houses and impute it. We are going to drop this area because garage we are not going to drop it. We are going to mark garage year built. I think we can drop it. We can impute it for 0. So before dropping it, we have to see certainly if we check it here, most of the fans alien miscellaneous feature are it's around 80%, more than 80% of the data is null. So it's a better to drop it because it's not going to add any variance to the data. But let's try to see a correlation matrix to understand the dependency of data. So here we are going to understand two things. One, how each individual field is correlated with the sales price, and is there any existence of multipolarity among the independent variable or not. So from here we can see that this is the high green area. We are having high green area. So we can say that these two, if you see here, garage area build and garage cars and garage area, right? So these, it means that these area, these features has been derived from each others. So it is creating a multicollinearity, and we can drop some of the 2 out of 3 field, any 2 out of 3 field to prevent from creating a problem of multiple linearity. Here we can drop one of the field, either first floor SFT or total basement. Other things we can notice from here is that if you check it here, like garage area, garage cars, they are having a high correlation into the sales price. Also, we can say that total RMS above ground, full bath, green living area, and also first floor SFTP, total basement SFTP, basement fit in SF1, mass BNR area, year remove, and overall quality conditions. These are the top feature. They're having high correlation with the sales. But since some of the feature are like, if you check it here, we can drop it. So we are removing the null point. We are going to drop the null point from mass VNR area. And now we are, after dropping those columns, we have 70 columns and 1, 4, 5, 2 rows. So now we can see that we have cleaned the data here. So let's try to understand, is there any, we have already, after dropping the rows, see there is a dependency or we have something. So we can still say that I don't find any multiplicity here. But we can see that these are the top feature that are representing, I mean saying that they are having high correlation to the sales price. And we'll do some more analysis onto the data part. So let's see it. So we are dividing the numerical and categorical column into the separate data frame. And we are going to treat the outlier here. So we can see that most of the columns having the outlier. So we are going to use interquartile range to remove the outlier. So we are removing from the 75%, I mean 25 percentile to, we are going to keep only the IQR between the 25 to 75, and outlier above that we have to remove it, not remove it. Basically, we have to set the maximum value for that range. So for max value, so we are taking the 75% of quartile to set the maximum value. If data is above the 75 current percentile or quantile of the value, then we have to set to the max value and minimum value to 25 quantile. So after removing it, we can see that the outlier has been also removed. And then there is no null present. So this is some, we'll do some data histogram and the scatter plot, analyze the data further, and we can see how the data is getting spread across the graph. So we can see that the data is right askew. So we'll take a log transformation. And after taking the log transformation, we can say that skewness has been removed from the data. And we are going to plot some scattered plot here. And we can see that basement in SFT2 having a single data, and we can drop it. This is the discrete value. We can use it. We can also see that there is a correlation between the front edge, lot area, mass finish area, basement finish area, total basement. They are having the high correlation into the sales price. Other columns that we are having, this is also a single value. We can drop it. We can also drop these columns. Green living area, open to susceptibility to take. They are having correlation into the sales price. There is also some skewness in the data. We are not going to transform it because the target is to participant. We are going to show how we can use regularization with the linear regressions. So here we are going to do the data preparation for building the model. And so here we are splitting the data into the train and test part, and then we are doing the scaling. We are using the standard scaling. So what standard scaling do? It generally distribute the data across the mean center 0 with the standard deviation 1. And we have a scale train and test data. After scaling, we have defined one thing we have done. We are taking dummy. Yeah, so we have a lot of categorical value. We have to convert into the numeric value. For that part, we are taking the dummies. And after taking that dummies, we can see that. So we are having 1000. Now we have a 223 columns. And we are doing the model. We are building the model using the static model OLS library. It will give us the statistical about the models. So we are more interested adjusted R-square here. How well those features are contributing into the variance of the data. So we'll keep try to increase the top feature to build the model. And if you see that top 50, we are having the adjusted R-square is a 90. Here it's at 91. Let's keep on increasing. We are increasing the number of the feature. 91. 92. Let's keep on increasing. Keep on increasing. Keep on increasing. 100. We have seen that it is 85. And then we are doing the 100. So in 100, we can see that it is mostly around 93. We'll do one more check if it is increasing, still increasing or not. So if we check it here, it hasn't increased. So we have to go down and check it. So we have checked with the 95. So it's still 93 one. And we have checked for the 90. And it's a 93 G. So we can take, there's not much difference in between the top 90 feature and top 95 feature. So either we can use top 90 feature or top 95 feature to build the model, since the adjusted R value is not increasing after that. So there is no use of going to take 100 top feature, 100 and 15 feature. So we'll use either 90 or top 95 feature to build the model. So same things, we are taking top 95 features to build the model. Feature is nothing but a top 95 columns that will contribute most of the columns into the building the model. And here we have defined one model. It's a function that will build the model. So here we have to pass a model type is equal to ridge or model type is equal to lasso. And then we are passing the parameter estimator model. Either it will come as a ridge or lasso. Here we are checking the R2 score, and then we are checking the RMSE score. So here alpha is nothing but a value of the lambda. So that is the optimal value of the lambda. We can see that. So it will try to build the model with each of the combination of this lambda and give the best model that having the best score. I mean best estimator. We have already defined that. Give us the best estimator here and best params here. What is going to be best params? So for each regularization, we are having the value is equal to optimal value is 50 and R2 score as a 90% and RMSE square is a 0.12. For lasso, we are having the value of the lambda is equal to 0.001 and R2 score is around 90%, and we are having RMSE test is equal to 0.1. So we do not see much difference between the lasso and risk, but we'll pick the lasso as a final model because we have seen a lot of insignificance filled into the data, and Lasso helps to drop the insignificance features while building the models. So we are going to select the lasso with alpha 0.001, and these are the top value that we have figured out. We are sorting the value based on the, so these, so these are the coefficient we have chosen. So these are the model coefficient, and these are the top coefficient that is contributing most of the to model building. I mean, these are the top 10 coefficient. So that's all for today. Thanks for watching.